Hey guys, welcome back. This is Math 172, the final exam review. We're doing a vector application problem, and it's problem 21. Now, let's just talk about it. We have a river that's flowing southeast at 6 miles an hour. So there's a river, dig these artistic skills, that's flowing this way at 6 miles per hour. Right, and then into this river we put a motorboat that's traveling at 15 miles an hour at this bearing. So north 60 degrees towards the east at 15 miles per hour. And we're asked to find the true velocity of the boat. So that's going to be this vector that connects the two of them. Because 15 miles an hour is more than 6. And so this arrow should be longer, right? So this is 15 miles an hour. This is 6 miles an hour. And this is 45 degrees. And we're asked to find the true velocity. All right. So the first thing that we really need to do in order to add these vectors properly is determine their components. So let's talk about the river first. The river here, we know, is 6 miles an hour at 45 degrees, starting at south, going east. So that vector looks like this. And this is the x component, rx. This is the y component, ry. And this angle is 45 degrees. So just looking at this, we know that these will be equal in magnitude. And remember, to find the x component, it's r cosine theta. To find the y component, this is r sine theta. So this is 6 times the cosine of negative 45. This is 6 times the sine of negative 45. So then rx, 3 square roots of 2, this gives us negative 3 square root of 2. So again, writing the river's vector in component form, this is going to be 3 square roots of 2 and negative 3 square roots of 2. That makes sense because it's going east and south, so this should be positive and negative. Okay, great. Now we need to find the components for the motorboat. We know it's going 15 miles an hour at north, 60 degrees east. Again, we're going to call this M for the motorboat. Mx is going to be M cosine theta, and My is going to be M sine theta. So that's So this theta is supposed to be with the x-axis. So in this case, we're going to be using sine for x, and we're going to be using cosine for y. And it's because our angle is here. So this gives us my with cosine, and this is mx. It's opposite the angle, so we use sine here. So make sure you're always looking at your drawing. So this is 15 sine 60, and this is 15 cosine 60. So in vector form, the motorboat is 15 square root of 3 over 2 and 15 over 2. All right. So the true velocity then is equal to the river's vector plus the motorboat's vector. So that's going to be 3 square roots of 2 plus 15 square roots of 3, adding these x's, and then adding the y's. So negative 3 root 2 plus 15 over 2. This is the true velocity. So then we're asked to find, well, how fast is that? So speed is the magnitude of the true velocity, which is equal to the square root of true x squared plus true y squared. So that's the square root of this, so 3 root 2 plus 15 root 3 over 2, plus negative 3 root 2 plus 15 over 2 squared. And when you stick that into your calculator, you find that the speed is equal to 17.54 miles per hour. And the last question they ask us is about finding the bearing of the true velocity. We know theta is the inverse tangent of the y component over the x component. So this is the inverse tangent of 3.257 over 17.23. And so this gives us 10 degrees. 10.7 degrees. But remember, guys, the angle that it gives us is here. So if this is 10.7, then this bearing angle has got to be 90 minus that. So 90 minus 10.7 is 79.3. So north, 79.3 east. All right. So again, this is problem number 21, vector application problem. We're given the speed of the river, the speed of the motorboat, and asked to find the true velocity. Step A is finding the components of the river, which you do using cosine and sine. Part B was finding the velocity of the motorboat in components. Part C was finding the true velocity, which is the vector sum. It's all this business. Part D is finding the speed of the true velocity. That means take the absolute value. So it's the x component squared plus the y component squared and take the square root. And then the last part was finding the bearing. Now remember, guys, when you take the inverse tangent, you're always going to get the angle with the x-axis. But for bearings, you've got to have the angle with the y-axis. All right, guys, this is how you do a vector application problem. If it's giving you fits, please come into the ILC. We'll happily walk you through another one. Okay, thanks.